Chapter 4. Control Valve Accessories.
Next, we turn to digital controllers.
I'd like to introduce you to control valve accessories. Pneumatically operated valves depend on a device called a positioner, which takes an input signal from a process controller and converts it into actual valve movement or valve travel. Positioners generally come in three configurations. First, pneumatic positioners receive a pneumatic signal, typically 3 to 15 sig, translate this into the required valve position, and supply the actuator with the appropriate air pressure to move the valve to the correct position. Second, analog I/P positioners perform the same function, but they differ in that they use an electrical current, typically 4 to 20 milliamperes, as the input signal instead of air.
The third type, the digital controller, is very similar in function to the analog I/P mentioned previously, but it differs in that the electronic signal conversion is digital rather than analog. Digital products are further divided into three categories. In digital non-communicating types, a current signal of 4 to 20 milliamperes simultaneously powers the electronics and controls the output. The HART method is the same as the non-communicating type, but it also enables two-way digital communication using the existing analog signal wiring. Finally, the Fieldbus method receives digitally based signals and controls the valve position using digital electronic circuitry coupled with mechanical components.
Fieldbus technology enables two-way digital communication over the same wiring, which improves control architecture and product capability while reducing wiring. Additionally, using a single, integrated analog I/P positioner or digital controller instead of a combination of a pneumatic positioner and a transducer, two separate instruments, lowers installation costs. The real difference between digital and analog I/P segments is the ability to embed software commands into the device's memory. This allows for automatic configuration and setup of the valve, and most importantly, it enables two-way communication for process, valve, and instrument diagnostics.
This is the configuration of a modern control valve utilizing a digital valve controller.
There are several reasons why users choose digital valve controllers. They reduce loop commissioning costs, including installation and calibration, maintain loop performance levels through diagnostics, and improve process control accuracy to reduce process variability. Two aspects are particularly attractive. One is automatic calibration and configuration, which saves considerable time compared to traditional zero and spanning. The other is valve diagnostics, using a distributed control system, DCS, PC software tools, or handheld communicators. Users can diagnose the health of the valve while it is still in the line. FALDVUE instruments provide new diagnostic capabilities that can be accessed remotely.
Personnel on-site can diagnose the health of a valve through a series of offline tests with the help of the flow scanner system. The flow scanner consists of a portable, ruggedized computer along with travel and pressure sensors. These sensors are connected to the valve to conduct diagnostic tests while the valve is offline. Based on the results, a skilled maintenance technician can determine whether to leave the valve in the line or remove it for repair. Digital instruments enhance the service because the sensors are built into the device, making it easier to run tests at the appropriate times.
Now, it is possible to diagnose the health of a valve remotely via HART or Foundation Fieldbus. Online diagnostics enable predictive maintenance without disrupting the process. Thanks to these remote capabilities, valves can be monitored, and those who manufacture, supply, and service valves can now assist customers in diagnosing valve conditions to a level never before possible. Predictive maintenance offers additional savings for the customer. By observing the performance of the valve as it operates and watching for decline over time, users can predict when replacement or repair is necessary.
Next, we turn to positioner basics.
This is a detailed schematic of a positioner used for a diaphragm actuator.
Looking at the operating principle of the positioner through the diagram, the nozzle-flapper mechanism, the feedback beam, and the cam are the key components. When an input signal is received, the nozzle pressure changes, which is then output to the diaphragm via a relay to move the valve. The actual travel of the valve is compared back to the input through the cam and feedback shaft, and the direction of action is determined by setting the direct-acting or reverse-acting quadrants.
Now, let's introduce other control valve accessories. A top-mounted handwheel for a direct-acting diaphragm actuator can be used as an adjustable travel stop to limit travel in the upward direction, or to manually close push-down to close valves. Conversely, a handwheel for a reverse-acting actuator limits downward travel or manually closes push-down to open valves. Limit switches send discrete signals to distributed control systems, signal lights, small solenoid valves, electric relays, or alarms, with the cam-operated type being a representative example.
This is a manual handwheel mounted on top of a direct-acting diaphragm actuator.
This is a manual handwheel mounted on top of a reverse-acting diaphragm actuator.
Next, we turn to actuator accessories.
A volume booster increases the output flow of the positioner to improve the operation of actuators that are large in volume or require a fast response. The positioner schematic varies depending on the actuator type, distinguished between those for piston actuators and diaphragm actuators. Each schematic consists of the input signal, diaphragm, exhaust port, output to the actuator, and supply.
This is the configuration and connection schematic for a piston actuator type positioner.
This is a volume booster that amplifies the air volume to increase the response speed of the valve.
Cam-operated limit switches typically operate 2 to 4 individual switches based on the movement of the valve stem. These switches are housed in an assembly mounted on the side of the actuator, can be adjusted individually, and are available for both AC and DC systems. For the solenoid valve manifold, the proper solenoid valve is selected based on the actuator type and the desired fail-safe operation, and it can be used with double-acting pistons or single-acting diaphragm actuators.
This is a limit switch that operates contacts through the rotation or movement of a cam.
Next, we turn to pneumatic systems.
Supply pressure regulators, commonly called airsets, reduce the plant air supply pressure to a level suitable for positioners and other control equipment. Common reduced air supply pressures are 20, 35, and 60 sig. This regulator can be mounted integrally to the positioner, nipple-mounted, or bolted to the actuator.
This device regulates the pressure of the supply air and removes impurities through a filter and moisture trap.
Solenoid valves are used to implement the desired fail-safe operation. A pneumatic lockup system is a device that locks in and maintains the actuator loading pressure at the moment supply pressure is lost. When used with volume tanks, it can move the valve to a fully open or closed position upon loss of pneumatic air supply, and normal operation resumes automatically once supply pressure is restored. In fail-safe systems for piston actuators, the piston moves to the top or bottom of the cylinder when supply pressure falls below a predetermined value.
This is the configuration of a solenoid valve, which controls airflow via electrical signals.
This is a schematic of a lockup system used to fix the position of a piston actuator.
A volume tank, charged with supply pressure, provides loading pressure to the actuator piston when supply fails, moving the piston to the desired position. When supply pressure returns to normal, operation resumes automatically and the volume tank is recharged. An electropneumatic transducer receives a DC input signal and uses a torque motor, nozzle-flapper, and pneumatic relay to convert the electrical signal into a proportional pneumatic output signal. Nozzle pressure operates the relay and is sent to the torque motor feedback bellows to compare the input signal with the nozzle pressure. This transducer can be mounted directly on a control valve to operate the valve without the need for additional boosters or positioners.
This shows an I/P transducer installed on a diaphragm-actuated control valve.
Through the schematics of a lockup system for piston actuators and a typical fail-safe system, we can see how the circuit is configured to move the valve to a safe position when supply pressure is lost.
This is a schematic of a fail-safe system designed to return the valve to a safe state during an emergency.
Next, we turn to EP positioners and diagram.
Electropneumatic positioners are used in electronic control loops to operate pneumatic diaphragm control valve actuators. They receive a DC input signal from 4 to 20 milliamperes and convert it into a pneumatic output signal using an I/P converter, nozzle-flapper, and pneumatic relay. This output is applied directly to the actuator diaphragm, creating a valve plug position proportional to the input signal. The plug position is mechanically fed back and compared with the input signal. Using split-range capability, the full travel of the actuator can be driven using only a portion of the input signal range.
This is a positioner mounted on a diaphragm actuator that converts electrical signals to pneumatic signals to control position.
Digital valve controllers have built-in instrument and valve diagnostics within their firmware, sending alerts if problems occur with instrument mounting, electronics, hardware, or valve performance. When a HART-based handheld field communicator is connected to the digital valve controller, user-configured alerts and alarms are activated. These flags notify the user of the current status and potential valve or instrument problems. Typical alerts include travel deviation, travel limit, cycle count, and travel accumulation. Additionally, AMS ValveLink software performs tests to identify problems across the entire control valve assembly.
By utilizing valve stem travel feedback and various sensors on the instrument, including the actuator pressure sensor, the health of the control valve can be evaluated while the valve is still in service and fully operational. This helps pinpoint problems before the equipment fails, allowing for a response without disrupting the process.